6. Okay, we'll start today. So very good morning to all of you. So we'll start today the new unit called as a probability. So some of you already might have been studied this probability in your 11th or 12th science, those who are having a mathematics, right? So we know that the whole world is uncertain, right? The whole world is uncertain. Every time we predict some chances, some possibilities, right? Sometimes we can say that it is likely to rain totally, right? It is 60% chance that India will win World Cup. Like that, we used to put some percentage, some possibilities, right? There is a high percentage or 60 percentage to be recover in a COVID. 90% possibilities are there to be recovered from a COVID, right? So whenever we are talking about this, what does it mean? It giving a chance, right? Where we can predicting some possibilities, right? That is nothing but a probability. Some of the things we are telling that it may happens, we don't know. It is a degree of uncertainty. Probability is nothing but a degree of uncertainty which we are going to measure. So that uncertainty we will calculate by using some theories or some basic definitions of the probabilities. Probability is nothing but a probability means possibilities. What is the chance to get or to lose or to what will happen in prediction? We don't know the results, but we can predict the results, right? Based on the probability theories. There are some standard things are there. I will come later on. Let me share my screen so that we can go through this. Yeah, so we are going to cover these things in today's class. So these are the basic things. Already you might have been studied in your 11th and 12th. What is the probability, definition of the probability, and some of the basic assumptions of the probability. Also some basic definitions about the sample space, event, random event, like that. And we require, while doing all this, we require the another kind of things called as a permutation and combination to solve some of the examples. We will not go so many examples, only we can solve some basic examples to get an idea. So we will not do like what you did rigorous examples in your 11th and 12th. We have to just get to know that what exactly this probability, what probability talks about, right? What are the basic assumptions of the probabilities, what are the basic rules of the probabilities, right? And what are the terminologies are involved in the theory of the probabilities. Just to we'll go through that, and based on that we will solve few examples so that the concept should get clear. And then we will use all this probability theory in our future studies to study our distribution, probability distributions, right? So to understand that concepts, we require these basic things. So that's why we have to go through all these terminologies or definitions, some examples like that. So the theory of the probability has its origin in the games of chance related to a gambling. Generally, in uh, before you can say in the 19th century or 18th century, this probability they mostly uses in a gambling, right? Why? When they used to play the cards, when they used to play the dice, right? Mostly in that cases they uses this probability. But later on, a scientist named as Cardon, who is a Latin mathematician, he wrote a book on all these things. The name as a book on games of chance. What is the possibility to win this game? What is the chance to lose this game, and which is published in 1663. Starting with the game of chance, probability has become one of the basic tools of the statistics. The knowledge of the probability theory makes it possible to interpret statistical result, since many statistical procedures involves conclusion based on the samples, right? So using the probability, we interpret so many statistical results using the knowledge of the probability. So probability theory is being applied in the solution of social, economic, business problems. Today, the concept of probability has assumed a greater importance, and the mathematical theory of the probability has become the basis for a statistical application in both social and decision-making research. Now, if you can, those who are willing to go in higher studies, in master studies, or those who are willing to do in management studies, especially I can say MBAs, right? MBAs or like HRMs. So they will have a special one paper which is on the statistics, where you are going to study all the things. Where if you want to make the decision, then again you have to use the knowledge of the statistics. Suppose you have a small company, right? You have a small company, and you will have supposed to be an 100 machines, and supposed to be a 200 workers, right? And we have to see that the optimization of machine, optimization use of machine and man resources and man hours, right? If you want to calculate all these things, again we have to take the help of statistics. Not only that, suppose if you are producing one product, supposed to be in a Mumbai, or supposed to be in any metropolitan cities, or in some big MIDCs, and if you want to distribute your this product, supposed to be in a cold drink, right, or supposed to be in a milk product, supposed to be some fast foods, if you want to sell or distribute this product in a different parts of the either city or in a state or in a country, then what are the smallest distance so that you can reach to that point with minimum time, right? If you want to calculate these things also, you requires statistics, that is called as an transportation problems, especially we call it as a transportation problems. Already I have given one more example that called as an assignment problem. Means we have to assign some job of some workers on some machines, right? Suppose there are 10 machines and 20 people are there. So how you are going to assign them work? So if you want to study, and so that you should get a more produce or more product in a day or in hours, so in that case also you have to use the knowledge of the statistics. So for that we require the statistics. Already in the social problems we are using the statistics for so many things. So these are the uses, and in that cases you require the again knowledge of the probabilities. So let us go with some basic definitions of the probabilities. First is a random experiment. The word itself explains what does it means. Random experiment is one whose results depend on the chance. That is, the results cannot be predicted, right? We don't know what is going to happen, but we are operating the event, or we are acting, or we are doing some activities, but we don't know what results is going to happen. For example, tossing a coin, right? If I will toss the coin, I don't know what results I am going to get. Either I will get head or tail, right? So that experiment is nothing but random experiment. That activity is nothing but the random experiments. So these are the examples. Or there are so many balls in a urn, There are red ball, orange ball, white ball, black ball, so many. And if you want to pick up any ball out of it, that event, that activity is nothing but a random experiment. Trial. What is the trial? Performing a random experiment is called a trial. What activity we did, that is nothing but a trial. Outcome. The results of the random experiments are called its outcome. Right? I'm throwing a coin. Right? I'm throwing a coin. I don't know what results I'm going to get. Right? After getting a result, surely either I will get a head or I will get a tail. That is nothing but our outcome, right? Here the example is given as when the two coins are tossed, right? The possible outcomes are there, right? If I can toss the two coins simultaneously, then what possibilities are going to happen? So the possibilities will be like this: the both may possible as an head, both kinds, it is possible. One coin will be head, another coin will be tail. First tail, second head, both tail, right? So these are the possibilities, and whatever these are the possible outcomes after performing an experiment, after doing a trial. So you will get these kind of results. That is nothing but the outcomes. Event. An outcome or a combination of outcomes of a random experiment is called an event, right? So whatever the experiment we did, that is nothing but again event, an outcome, right? Suppose uh, later on I will explain again, I will come with that. For example, tossing of a coin is a random experiment, and getting head or a tail is an event, right? If I'm toss the coin, so there are two possibilities: either I will get head or tail, right? So getting head is one event, getting tail is another event, right? So like this, in earlier example, we can have a different events here, right, on this. So I will explain again here more precisely that same event. The next definition is a sample space. What is the sample space? It is again a set of outcomes. Simply, if you want to say that, it is a set of outcomes, right? What are the possible outcomes are there? If I will make them, will keep them in a set. That is nothing but a sample space. The outcomes of an experiment is called a sample space. Suppose I'm tossing a coin. What are the possibility? Getting head and tail, right? Getting head and tail. So this is my sample space. This is nothing but my sample space. Suppose I'm tossing a two coins, right? Suppose if I toss the two coins, so what are the possibilities? So these are the possibilities, right? So now this is my sample space when I am tossing two coins, right? So what are the possibilities? Sorry, this is for three coins. So for two coins, what is the possibility? Either I will get both heads, either I will get both tails, one head, one tail. Is it visible? Yes, Nitu, you can respond. Is it visible?
Yes, sir.
Wow, thank you. So, if I cost two coins simultaneously, so what are the possibility? I can get the two heads, I can get two tails, I can get head and tail, and I can get tail and head. So these are the possibilities. So this set we are calling as a sample space. We are calling this as a sample space. Suppose if I will toss three coins simultaneously, so what will happen? So these are the possibilities. So total these are the 8 possibilities. So if I toss one coin, I am getting two possibilities. If I toss two coins, I am having four possibilities. If I am tossing three coins, I am having a eight possibilities. Right? So what are these possibilities? I already noted here. First heads, all may be heads. First two heads, one tail. First head, last two tails. Head, tail, head. Tail, tail, tail. Tail, tail, head. Tail, head, head. Tail, head, tail. Right. So these are the possibilities when I am tossing a three coins simultaneously, and these possible outcomes we are calling as a sample space. Now another example, suppose generally we while playing some different games, we use this dice, right? So that dice is nothing but a another possibilities. I don't know if I will throw the dice, what outcome I am going to get, right? That is unpredictable. So what are the possibilities? I may get one, I may get two, I may get three, four, five, or six. So these are the sample spaces. These are the sample spaces, possible outcomes of my random experiments. And if we will collect all these possible outcomes and if I will write it in a set form, so that is nothing but my sample space. Is it clear? I think. Yeah. Now there is another definition called as equally likely. Two or more events are said to be equally likely if each one of them has an equal chance of occurring. Right? If each them of having a chance coming as a same. For example, in a tossing of a coin, the event of getting a head and the getting a tail are equally likely events. Right? Both having the same possibilities. Means 50-50%. Getting head also 50%, getting tail is also 50%. So next is mutually exclusive. Two or more events are said to be mutually exclusive when the occurrence of any one of the event excludes the occurrence of the other, right? When we can say that equally likely if both having a same number of or same percentage of possibilities. If when we can say that mutually exclusive when the occurrence of any one events excludes the occurrence of the other events. So mutually exclusive events cannot occur simultaneously. So here example is given that when a coin is tossed, either the head or tail will come up. There is no possibility that both will come at a time, right? The getting head or tail in a tossing a coin is a mutually exclusive event. So next definition is that exhaustive events, right? Events are said to be exhaustive when their totality includes all the possible outcomes of random experiments, right? If all the possible outcomes are there, then we can say that that event is exhaustive. Means all the events we are putting their sample spaces, then you can say that that event is exhaustive event, right? For example, while throwing a die, these are the possible outcomes. So we are quoting all the possible outcomes. Similarly, we did here. Similarly, for one coin, two coin, three coin, and one dice. Right. So this is nothing but these are the exhaustive events. Complementary events. It is the same like addition and subtraction. Right. Complement of A. What will be that? Subtraction, like that. The event A occurs and the event A does not occur are called the complementary events of each other. Right? The event A does not occur is denoted by A in cap C or A dash or A bar. These are the notations to denote the complement, right? Suppose if you will have this whole A, right, and suppose this is your total set. Suppose this is your universal set, and suppose this is your set A. Then what is the complementary of A? What will be that? That complementary, right? You will take out from that A universe and you will get that A complement. And generally we denote it as by either A bar or A C or A dash. So these are the notation to denote the A complement, right? So these are the examples. In a throwing a die, the event of getting odd number is 1, 3, 5 and getting the even number is 2, 4, 6. So these are the complements of each other, right? Suppose this is your universal set, and what will the outcomes? Outcome will be 1, 2, 3, 4, 5, 6, right? And suppose A is equals to an even number outcome as an event you consider, then what will be the event A? 1, 3, 5. These are for odd numbers. Then if you can take the complement of odd numbers, so you will get the even number. Means 2, 4, 6. These are the chances of A complement event, right? So these two events are called as mutually exclusive and complement to each other. Next is independent event. Events are said to be independent if the occurrence of one does not affect the other, right? Means whatever the events are there, suppose just which we have quoted one example, that tossing a die, right? So what will be the sample space? Sample space will be this, right? Then number of even numbers, outcome of even numbers and outcome of odd numbers, there will not be effect of each other, right? So such a events we call as an independent events. The occurrence of one does not affect the other. In the experiment of tossing a pair coin, the occurrence of the event head in the first toss is independent of the occurrence of the event head in the second toss or a third toss or subsequent tosses, right? So that is nothing but a independent event. So let us see the definition of the probability which we generally uses, right? Is nothing but, generally we denote it as an P of A. What is A? A is an event, right? Probability of getting event A, we can say in general this, right? And what is this M? Here it is already written. M are the favorable to the occurrence of a event A. Favorable chances, the chances which tends to what we want, and divided by N. What is N called? N is called the probability of occurrence of the, sorry, total number means sample space. That is nothing but a sample space. Total number of exhaustive cases. So for finding the probability of an event A is nothing but number of cases favorable to event A and total number of exhaustive cases. So there are few assumptions we have to do whenever we are talking about the probabilities. So what are these assumptions? Let S be a sample space and A be an event in S, right? And P of A is the probability satisfying the following axioms. So probability of any event has to satisfy these following assumptions. The probability of any event ranges from 0 to 1, means probability will not cross 1. Always it is lies between 0 to 1, right? So if while doing some calculation or solving some problem, suppose if you are getting your answer either left side of 0 or right side of 1, so you have to confirm that you did somewhere wrong calculations, right? Means probability will not exceed 1, right? That is the second. The probability of the entire space is 1, right? What is the next one? If A1, A2 and so on are the events on a sample space N, and if you take the union of all probabilities is nothing but their addition of individual probabilities, right? If you suppose S is in a sample space, and if we have different events on S, for example, suppose we have uh, say that experiment as random experiment as tossing two coins, or tossing a die, playing with a die. If we throw a die, so the total outcomes are this: 1, 2, 3, 4, 5, 6, right? So what is, suppose there are two events. Suppose event A is equals to, or in this language you can say A1 supposed to be getting an odd number, and A2 getting an even number, right? So the probability of A1 union A2 means probability of getting odd numbers and even number is same as probability of getting odd number plus probability of getting even numbers, that which it says, right? So there are some statistical interpretations are there. So yes, always we uses this S as a sample space. Always the notation yes we use for the sample space. A bar means A does not occur, or it is says a complement. A union A bar is nothing but again whole sample space. Their intersection is phi. There is a event A and their event is B, and suppose their intersection is phi, then we can say that A and B are mutually exclusive. And if their union is phi, then you can say that event A occurs or event B occurs, or both A and B occurs. If their intersection is nothing but both the events A and B occurs, and if they are complement, then both are not occurring. So here is a addition theorem is there. The same what usually we uses in a set theory, the same is applicable in case of the probability as well. So if two events A and B are mutually exclusive, the probability of occurrence of either A or B is nothing but the sum of the individual probabilities of A and probability B. So A union B is nothing but, here also you have to write probability of A union B. I think I missed this, is equals to nothing but the probability of individual events. If two events A and B are not mutually exclusive, then the probability of event is either A or B or both occurs is given is nothing but it is the same rule where which rule we have seen in our set theory, right? Probability of A union B is nothing but probability of A plus probability of B minus intersection of probability of A intersection B. So another definition is called as a compound events. The joint occurrence of two or more events is called as a compound events. The compound events imply the simultaneous occurrence of two or more simple events. So what are the examples? These are the examples. Tossing two fair coins simultaneously, the event of getting at least one head is a compound event, as it consists of joint occurrence of two simple events. Event A is nothing but one head appears, right? So we are tossing a two coins, so this will be the sample space. So what is the event A? One head appears. So what are the things here? in these two cases, one head, one tail, another head. So these are the two possibilities. Or similarly, event B, two heads appearing, only one. So similarly, if a bag contains 6 white, 6 red, and we make to draw of two balls at random, then event that both are white or one white, one red are the examples of the compound events. So there are so many basic definitions are there. So there are one more might be definitions after this. So independent and dependent events. The compound events may be we have classified into two different dependent and independent events. If two or more events occurs in such a way that the occurrence of one does not affect the occurrence of the other, then we can say that these events are independent. If a coin is tossed twice, the results of the second throw would in no way be affected by the result of the first throw, right? So there is no any relation, either what thrown you have did for first one and second one. So that kind of events you call as an independent event. So what is the dependent event? If the occurrence of one event influences the occurrence of the other, then the second event is said to be a dependent on the first. If we do not replace the first ball drawn, this will be chance the composition of ball in the bag while making the second draw. Right? Suppose just which example we have taken last time, 6 white and 6 red. So first draw if you did and again you put it the same ball in that bag, then there is again chance to get the same kind of combination. So that is nothing but a dependent event. So there are some multiplication theorem on the probabilities for independent events. If two events A and B are independent, the probability that both of the occur is equal to the product of their individual probabilities. So probability of means there are two events which are the independent, then probability of A intersection B is the same as probability of A into probability of B. So these are the basic definitions which we will may use for solving different examples or to understand the different concepts. So let's move to the one more important thing which we require while next calculations called as factorial. Factorial means what? It is the consecutive product of first n natural numbers is known as a factorial. So generally we denote the factorial as a notation n factorial. We call it as we read this as this notation as n factorial. So what is the n factorial? N factorial is a product of first n natural numbers, 1 cross 2 into 3 into 4 into 5 up to n. For example, what is the 3 factorial? 1 cross 2 cross 3. So it is equals to 6. So what is the 4 factorial? 1 cross 2 cross 3 cross 4. Similarly, 5. Right? So this is the definitions of the factorial and example. So let us move to the another definition called as permutation. Permutation means arrangement of the things in a different ways, right? So either permutation and combinations, we will make the combination and make the arrangement. Both are the difference. I will come to later on what is the difference between a permutation and combination. Let us first will define and we'll try to understand what is meaning the permutation. It is the arrangement of n things r at a time, right? Suppose you have n things and we are going to arrange r things at a time. That is nothing but permutation of, and generally we denote it as by npr, and we defined it as n factorial upon n minus r factorial. Let us see one example of this. Suppose there are three things A, B and C. Taking two at a time, right? So we have to take two things at a time. So we can arrange uh, this idea or this experiment as there are three things, we have to take two at a time. So what are the possibilities and combination chances are there, arrangements are there? A B, B A, A C, C A, B C, C B, right? So here we find the six arrangements, right? In this arrangements, order of the arrangement is considered. The AB will not be equals to BA. But if in a combination, if you will go in a combination, AB is the same as BA, because it is a, like a commutative law. Commutative law holds in a combination, it will not hold in a permutation. Simply you can say that in that way also, right? So here there are six arrangements we can do different way. There are three things taken, two things at a time, and we can arrange them in this way. So the number of arrangements of the above given number of a permutation of three things taken two at a time. Generally we use this in our day-to-day lives. What kind of permutations you are going to do means what kind of arrangements you are doing, or what kind of arrangements are in your mind, so that it is the same. So if you can see that if you are taking out of three things, two things at a time, so how many arrangements we can do? You can do the six arrangements. So symbolically if you want to write, it is a 3P2, three things are there and taking two at a time, so it is nothing but a six types of the arrangements you can do. So there is another alternative is there, means same we can write in different way. Thus the number of arrangements that can be made out of n things taken r at a time is known as the number of permutation of n things taken r at a time, and it is denoted by same, and we can write. So earlier in this definition we wrote factorial in a fractions, right? Numerator and denominator. But similarly, we can, by doing some arrangements or by some manipulations, so we can write as NPR is nothing but n into n minus 1, n minus 2 and so on, n minus r minus 1. So let us, based on these things, we'll solve simple example. See 10P3, right? Now rather than using this definition, I will use this result, right? So what will happen? 10, 10 minus 1, 10 minus 2, right? So it is nothing but 10, 9, 8. So you have to take consecutive numbers up to 3. These are the descending order of 10 consecutive numbers, 10, 9 and 8. So suppose we can solve the ultimate, the answer of this is this. So if we can solve by the earlier definitions, which is the one we have given earlier, 10 factorial upon 10 minus 3 factorial. So what will happen? 10 factorial means you have to multiply 1 cross 2 cross 3 cross up to 10, and 10 minus 3 means 7 factorial, 1 2 3 up to 7. So now here you can see that, so what is happening? 10 factorial divided by 7 factorial, which is the same as, it is nothing but 1 cross 2 cross 3 cross 4 cross 5 cross 6 cross 7 cross 8 cross 9 cross 10, right? Similarly, what will come in a denominator? Denominator will come 1 cross 2 cross 3 cross 4 cross 5 6 and 7, all right? So now what will happen? This up to this, it will cancel straight away. So what will be remain? Remain will be this part. So this is nothing but again 8 cross 9 cross 10, which is the again 720. Means we are getting the same kind of result by both the ways, right? So now let us go to the another definition called as a combination. Here is also same. How there are n things are there taking r at a time. So how many combination how you can do that, right? The combination is a selection of an object without considering the order. So in a combination, order is doesn't matter, but in case of permutation, order matters. That only you have to keep in your mind. And how we can define ncr is equals to n factorial upon n minus r factorial into r factorial. So similarly, we know that this combination, this is nothing but npr. So we can replace this as an npr and divided by r factorial. And there are some results are there. nc0 is 1, nc1 is equals to n, and n things if you can take an n at a time, that will be their combination will be 1 only. N things you take a 0 time, there is a 1 combination. N things taken 1 at a time, there will be n combinations will be there. Now this is the same example. There are 3 things, say a, b and c, right? And if we select any 2 things, right, then there are combinations will be like this: ab, ac and bc. So in this case, ab is equals to same as a ba, ac is equals to same as ca, bc is equals to same as ca. These are the only combinations, right? So here order doesn't matters. So those who attended so many uh, competitive exams, they might have been gone through such a kind of examples, right? There are 3 boys are sitting, or 2 boys and 3 girls are sitting in a row, 1 girl and 2 boys taking at a time. So what is the combination or what is the permutations? Some example based on such a kind of things may appears in such a kind of different exams, right? So here is another example. See here, which I said, no, I didn't give that result. So this result again we have used here, 10C3 and 10C4. How we can find? Just I did the manipulation again. Same. We can write same. It is a np3 upon 3 factorial, and we know that np3 is nothing but take 3 consecutive numbers descending order from 10. So 10, 9, 8. And 3 factorial is nothing but 1 cross 2 cross 3. So this is nothing but 720, which is already we have seen in earlier example. 720 divided by 6. So it is 120. So this is another example, 8C4. Now you can see here 10C7. 10C7. So from this we can make a general result that n things taken r time is same as n things taken n minus r things will be the same. 10C3 is same as 10C1. So this is the another relation between the combinations. So keep in mind that you may use this result in a future. So this is the example of combination. Suppose we have to select a cricket team of 11 members. So and suppose there are 13 players are there. So in how many ways we can do these things? So that is nothing but 13C11. We know that 13C11 is same as 13C2, and that is nothing but 78 combinations we can do. So these are the famous examples in probabilities. That's why I have given their pictures based on the coins, based on the dice, based on the playing cards. So there are will be 52 cards. Suppose what is the probability to get all hurt? What is the probability to getting a queen? Right? Like that. So a bag contains different colors of balls, right? And suppose I am choosing 3 balls randomly. So what is the possibility to getting 1 red, 2 green, 3 yellows, 1 white, like that. So all these are the combinations. So mostly the probability theory or most the examples are based on these 3 events or these 3 things, either on a coin or a dice or the playing card or these things. So that's why I thought to give the pictorial representation. So let us see one example we can solve here, and after that we can stop because I have to go to attend a EMA orientation program today. Okay, let's first we'll finish this. So 3 coins are tossed simultaneously. Find the probability that first no head, 1 head, 2 heads, at least 2 heads, and at most 2 heads appear. Right. So what is the sample space? Sample space is already I have wrote. Suppose if 3 coins we can toss, so these are the possibilities, means number of sample space is nothing but 8. So now what is our first event? First event is telling that there should not be any head, no head event I want. Means what possibilities remain? All should be tail. That is nothing but number of A is equals to 1. So what is the probability? Number of the favorable outcomes divided by number of sample space. So 1 upon 8. So 1 head. So 1 head, what are the possibilities? Head, tail, 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 head, head, tail, tail, head. So number of B means event B is nothing but 3. So what is the probability of that getting? 3 by 8. 2 heads. So HT, so again it is a 3, and you will get the probability for this event is 3 by 8. At least 2 heads. Alright. So there is a 4 possibilities are there, and possibility of this event is nothing but 4 by 8 means it is 1/2. Almost half possibility is there, at least getting a 2 heads. At most 2 heads, so there is a this much of possibilities there. If you can see anywhere the probability is not crossing 1, it is not less than 0. Sorry, below of the 0. So this is the as an examples. Now so today we'll stop here. You can go in 11th 12th probability books and you can find so many examples for your as an test problems. If possible, I will upload on the TESOL some of the examples so that you can solve some of the examples and get through that. So we'll stop here today. Again, we'll meet in a next class. If you have any doubts and any problems, so we can discuss in next class, because today is our MA first year orientation is there.